Hello YouTube and welcome back to this channel. Today we are looking into the expression I to the power of I. Here I refers to our complex identity. And the result will really surprise you, so stay tuned if you're interested. And remember, if you enjoyed this video, please hit the like button, comment down below, and if you haven't subscribed to this channel, please do it so that we'll stay tuned with more content like this. Without further ado, let's go right into it. So let's set x equals I to the power of I, and we are looking for this x. So then we can write I to the power of I as e to the power of I times the logarithm of I. So we can always do this when we have some exponential expression like this. So we reduce the task of finding I to the power of I to let's find I times the logarithm of I. So in order to find out what this expression is, we need to find out what is the logarithm of I. And in order to find it out, we note that the e function is the inverse function of the logarithm. So in order to find a certain value when we are evaluating the logarithm at some point, then we try to find a certain y as a complex number such that e to the power of y equals I. So as you can see, we reduced the task multiple times to some other tasks, and now we are ending up with, for what values y, where y is a complex number, we have e to the power of y equals I. So let's use Euler's formula here, which states e to the power of I times t equals the cosine of t plus e times the sine of t, where t is a real number. And now by comparison of what we are having here at the top with this formula, we have to find t from the real numbers such that, firstly, cosine of t equals 0, and secondly, the sine of t equals 1. Yeah, because then in this case, the real part of this complex number here is 0, as we have it here, as what we are looking for, and the imaginary part is here 1. And that's exactly what we need because we have I. So, and when drawing, and I'm really bad at drawing, excuse me, but I will try my best. And you see now that for t equals pi over 2, the cosine, which is this one, attains exactly 0. That's what we need. And gladly, sine attains 1 here, right? So, we have found 1t where this holds. And just for your information, as sine and cosine are periodic and the periodization is 2 pi, there are infinitely many t's that fulfill these equalities, namely pi over 2, that's what we have found, plus 2 pi, because both functions are 2 pi periodic, times n, where n is any integer. But for this task we just need pi over 2, and that's good enough. And now we can plug this in into this equation here, into the third one, to get e to the power of I times pi over 2 equals I. And from this it follows, see here this second equation, y equals I times pi over 2. And as y was our ln I times pi over 2 equals ln I. And now we can plug this in into our first equation and get I to the power of I equals e to the power of I times ln I. And as you have just seen, ln I is I times p over 2. So we have e to the power of I times p over 2, which is e to the power of minus p over 2. And this is very interesting. E to the power of e, two complex numbers, and you are taking a complex number to the power of another complex number. Here we have 2 times the same complex number, results into something out of nowhere, e to the power of minus pi over 2. Very interesting. So again, as in Euler's identity, you have very important mathematical identities here together in one formula. I to the power of I equals e to the power of minus pi over 2. Very interesting, crazy. So I hope you enjoyed this video as I did. And if yes, stay tuned for more videos like this. See you next time. Bye bye.